basic examples of metric spaces now well understood, let us proceed and give plenty of definitions. I once again urge you to connect each and every concept introduced in this module with the corresponding concept defined for the real numbers in the earlier chapter entitled A Taste of Topology. So the first definition is going to be that of a sequence. Definition: let X be a metric space. A sequence in X is nothing but a function f from the natural numbers to X. No surprises here. As usual, we shall use the notations xn, n coming from n, or xn, n coming from n, or just plain xn to denote sequences. All of these denote sequences. Fine. Now let's come to the most important definition of convergence, and again it will be no surprise because you have already seen and spent a considerable amount of time digesting this definition. Let xn be a sequence in the metric space X. We say xn converges to x0, where x0 is an element of X if for each epsilon greater than 0 we can find n epsilon in the natural numbers such that if small n is greater than n epsilon, then d xn x0 is less than epsilon. What this definition is saying is that whenever this n is chosen suitably large, then the distance between xn and x0 can be made arbitrarily small. The definition is exactly analogous to what we have already seen, digested and assimilated in our bloodstream, the earlier concept of convergence that we saw for real numbers. Now let me just make a remark. We will continue to employ descriptive language for limits of sequences. What do I mean by continue to employ descriptive language for limits? Well, I urge you to look through the corresponding section in the chapter on sequences and series that we saw before in Real Analysis 1, but let me just recall one major phrase that comes up repeatedly that it is worth rewriting once more, even if it is going to be a repetition. We recall that the phrase P of n is true for sufficiently large n is just a shortcut for saying there exists n such that if n is greater than capital N, then P of n is true. Okay, so the tedious and complicated expression is just shortened to saying Pn is true for sufficiently large n. So the definition of convergence just reads xn converges to x if dxn x less than epsilon for suitably large n. Okay, of course I must write x if for all epsilon greater than 0. Okay, so I once again urge you, please go back to the section on sequences and series in the chapter on topology on real numbers and revise all the basic concepts that we have introduced. It's going to be used without further description in what follows. Okay, now what we are going to do is study some more definitions, but it might be worthwhile to pause and work out a couple of exercises to make sure that you understand what exactly is happening in this more abstract and general setting of metric space. Again, to ground our knowledge, it might be a good idea whenever a new definition is introduced to look back in the corresponding chapter on real numbers. But of course, just seeing that concept in the real numbers is not going to be fully will not enable you to fully understand and appreciate this more general theory. So what we should do is look through some examples which are far away from real numbers also, so that we have a good understanding of these definitions. So let me give you an exercise that will cement your understanding of sequences and convergence. Let X be a set with the discrete metric. That means this X is a trivial metric space. When does a sequence xn in X converge? Think about a discrete metric space and consider a sequence xn. In this discrete metric space, can you precisely describe when the sequence will actually converge? Is there any easy way to just look at the sequence and tell whether it converges or not? Solve this exercise. Next, another exercise. Suppose we consider the metric space B close 0 1 R. Okay, so this is the metric space of bounded functions from close 0 1 to R with the sup norm metric, of course, with sup norm metric. When does a sequence Fn in X converge to F in X? Think about when this will happen. Okay, so please solve these two exercises. It will give you a grounding in the notion of convergence in this more general setting of metric spaces. Okay, onwards, definition, and this is an important definition of continuity, but as we have digested this definition as well, it's not going to prove that much of a challenge. Let X and Y be metric spaces with a function f from x to y. We say that f is continuous continuous if for each sequence xn in X such that xn converges to x in X, we have fxn converges to f of x in Y. So a function from a metric space X to a metric space Y is said to be continuous if whatever sequence xn you take that converges to some x in X, we have that the limit, the image sequence fxn converges to the limit f of x. Okay, if you recall, this was one of the characterizations of continuity that we have already seen for continuous functions from a subset of real numbers to real numbers. We have already seen several characterizations of continuity, and this is one of them. Okay, in a later module, we will characterize continuity in terms of open sets as well. So for the time being, you can solve one exercise. Formulate the definition of continuity at a point. I'm going to leave it to you to figure out what exactly this question is asking you to do. The moment you figure out what this question is asking you to do, actually solving the exercise will be over. So I don't want to spoil the fun, so please think about this and do it. Some more definitions. So as I mentioned, this is going to be a long list of definitions, most of which you have already seen in the chapter on topology of real numbers. Definition: a sequence xn in a metric space X is said to be Cauchy if for each epsilon greater than 0 we can find n epsilon in the natural numbers such that if n comma m is greater than or equal to n epsilon. It doesn't matter whether you write greater than or equal to. Just for spicing up things, I'm writing greater than or equal to here. If you really understand what the definitions are saying, this shouldn't really bother you. So such that if n comma m greater than or equal to n epsilon, we have d xn comma xm is less than epsilon. So this just says that the distance between terms of the sequence become arbitrarily small if n comma m are sufficiently far. Okay, so intuitively, a Cauchy sequence is one in which the terms of the sequence start getting closer and closer to each other as we move towards the tail of the sequence. The same proof that you have seen will show that convergent sequences are Cauchy, which I'm going to leave as an exercise. Convergent sequences are Cauchy. The exact same proof will work word for word. But one interesting remark that can be made is the converse is not true. The converse is not always true. It is not true that if you have a Cauchy sequence in a metric space, then it converges. That's not necessarily true. A simple example should clarify what is happening. Just look at the set A comma B subset of R. Just the open interval A comma B in R. Now what we can do is we can treat A comma B itself as a metric space by just considering the same absolute value function as the metric on AB. Okay, then it will be clear to you that the sequence A plus 1 by n, we may have to start n suitably large, but that really doesn't matter. I leave it to you to formulate this example precisely. Look at the sequence A plus 1 by n. We know that this sequence is Cauchy. In fact, this A plus 1 by n must converge to A, but if you notice, this A is not actually an element of AB. It's not an element of AB. It's an element of R, but our metric space itself does not have the point A. So what this is saying is you can have a Cauchy sequence that does not converge to any point in the metric space. Okay. So let me give one more definition in this regard. Definition. A metric space X is said to be complete if any Cauchy sequence in X converges. Okay, so as you can probably guess, we have already proved this. R with its usual absolute value as the metric is clearly complete. In fact, this notion of completeness that we have just defined is actually equivalent to the completeness axiom that we spent a considerable amount of time studying in the context of ordered fields. So this is just a remark that is not really central to this course, but I just want to make that this notion of completeness, which is sort of a topological completeness, is actually sort of equivalent to this algebraic completeness that we saw when we studied ordered fields. Okay, sorry, scratch that remark. Not algebraic completeness in the sense of an ordered field that we define. Algebraic completeness means something else. Sorry about that. Algebraic completeness means that every polynomial has a root. Somehow I got the things mixed up. Sorry about that. So let's come back to this notion of completeness. R is a complete metric space. Work out these two exercises to understand this notion of completeness in greater depth. Exercise: what are the Cauchy sequences? In a discrete metric space. And the second exercise is, can a discrete metric space be complete? Solve these two exercises, then you will understand what exactly is going on with completeness. Okay, onwards and forward. Another definition. Let X be a metric space. And A subset of X. Okay. Now we define the diameter of A to be the supremum of dxy such that x and y come from A. Okay, look at all pairs of points that come from A, look at the distance between the pair of points and take the supremum. Okay, now the second part of the definition is more important. We say the set A is bounded if diameter of A is finite. Okay, so whenever the diameter of a set is finite, then we say that the set A is a bounded set. Okay, now again another exercise for you. Plenty of things in this particular module is going to be left as exercise, because as I have mentioned repeatedly before, much of this set of definitions and basic theorems are just obtained by changing notation in the earlier chapter on topology of real numbers. Any Cauchy sequence is bounded. Any Cauchy sequence is bounded. Okay, so let me give one more definition and related to this notion of diameter. Definition, let X be a metric space. Let X be a metric space. And take a point X in X. We define the open ball of radius r greater than 0, centered at X to be Bxr is by definition the set of all y in X such that dxy is less than r. The definition is completely self-explanatory, and again it's more or less exactly same as the definition of open balls that we have already seen for the real numbers. Okay, one exercise in this context is the following. Exercise show that open balls are always bounded. It's rather a trivial exercise. You can even figure out what the bound is. But show by example that the diameter of an open ball is not always twice the radius. So you will have to cook up a metric space in which it does not hold true that if there is a ball, then automatically the diameter of that ball is twice the radius of that ball. That's not going to happen in this particular metric space. Okay, once we have defined open balls, the next definition should be fairly clear to you. In fact, I expect you to have guessed it. Definition, again, I'm getting sick and tired of writing let X be a metric space, so I'm going to take it for granted. Okay, let S subset of X, we say X in S is an interior point if Bxr subset of S for some r greater than 0. Okay, and the next definition is also going to be utterly self-explanatory. Let U subset of X, we say U is open if each point of U is an interior point. So far so good. All the definitions as I had promised are just change in notation of the earlier definitions. And more to follow, which you should have anticipated again. Definition. Let S subset of X. We say X naught in S is an adherent point of S if we can find a sequence xn such that xn is in S and xn converges to x naught. Okay. If furthermore we can choose xn such that xn's are all distinct. This just means that there is no repetition. In this sequence. Then we say x naught is a limit point. An adherent point that is not a limit point is called an isolated point. An adherent point that is not a limit point is called an isolated point. And the last definition is the closure of S. S closure is the set of all adherent points of S. Okay, so all these definitions are word for word the same. If you are getting bored, don't worry, we are just a few more definitions away and then we can move on to more interesting material. Okay, yet another definition, this time that of a closed set. A set F subset of X is said to be closed if it contains all its adherent points. Okay, so just as a remark, I'm not going to write this down. In the literature, what we call limit points are often called accumulation points or cluster points. And again, the terminology is not consistent across textbooks. What we have called an adherent point, some authors call a limit point. So it's a bit confusing. I strongly recommend that whenever you pick up a textbook that uses these concepts, always check for when the definition of the author, what exactly the author means by limit point or adherent point or accumulation point or cluster point. It's always a good idea to double check. Okay, the last few definitions in this extended module of definitions. Definition. A subset S of X is said to be dense if S closure is equal to X. Okay, this is probably the only definition that is somewhat new. We have already seen it in some context, but this is probably the only definition, and this one and the next one to follow are the only definitions that are genuinely new. A metric space is said to be separable if it has a countable dense subset. Okay, so a metric space is separable if you can find a subset that is both dense as well as countable. Okay, we already know that Q closure, the closure of the rational numbers, is the real numbers, and Q is also countable, which we saw long ago when we were still in kindergarten. So we have seen that Q is also countable. Therefore R is separable. Okay. Now the final definition in this module. You must have seen isomorphic vector spaces. You must have also proved that any finite dimensional vector space is isomorphic to Rn. What this means is that this isomorphism sort of acts like a dictionary that translates the elements in one vector space to that of the isomorphic vector space. So isomorphic vector spaces are essentially the same vector space up to a renaming, and this renaming can be achieved by using an isomorphism. When are two metric spaces the same? Well, we have the following definition. Let xd and yd prime be two metric spaces. A map f from x to y is said to be an isometry if for all pairs x comma y coming from x, d xy is exactly equal to d prime f of x f of y. So from the perspective of distances, the distance between a pair of points in the space x is exactly equal to the distance between the image points f of x and f of y. Okay, therefore whatever holds true for a pair of points in the space x, the same property will hold true for the pair of points f of x f of y in the space y. So two metric spaces are said to be isometric if we can find a bijective isometry between them. Okay, so I'm going to leave you with an exercise. If f from x to y is a bijective isometry, of course x and y are metric spaces. I am not writing everything out in full detail. Suppose f from x to y is a bijective isometry. Show that f and f inverse are both continuous. Okay, so this concludes an excessively long list of definitions. I really thank you for your patience. This is a course on real analysis. and you have just watched the module entitled Loads of Definitions.